connected, of course, it has to be, with some of the optimization algorithms we've been thinking about. But I'd say like the academic lineage of these things are fairly different. There's a whole class of algorithms that come from sort of AI search, graph search, discrete optimization, cart pulls, quad rotors, and then starting to make things more and more complicated. So introducing contact made things more complicated. And the last lecture, we got many more degrees of freedom with our humanoid. Now that, in some way, the big point last time was actually that if you have enough degrees of freedom, some of the dynamics problems actually get easier. And I hope that point landed, that somehow you can start abstracting your dynamics into the thinking about the dynamics of your center of mass and your angular momentum, which are actually easier maybe than thinking about all your joint dynamics. Okay, but now that we've sprung a lot of limbs, a lot of joints, then we can get ourselves into more complicated situations. So I want to continue today with thinking about some of the complexity that comes with having lots of links. So for instance, Atlas, when we were working on Atlas a lot, Atlas had to do a bunch of things. It had to walk around, it had to turn valves, but it also had to solve relatively complicated manipulation type tasks with a lot of links. And the planning problem for pulling, this was in a disaster response scenario, and so the scenario was roughly that there was a door that you had to get through, and a bunch of 2x4s had fallen in front of the door, and you had to remove the 2x4s or power your way through. However, somehow you had to get to the door. And so the setting was roughly that you had to figure out how to pull out the 2x4s, get them out of the way, and get through the door. And so that's a pretty complicated motion planning problem where when you start playing these games of trying to find collision-free trajectories to pull a big 2x4 out of a pile in somehow minimal way, minimally disruptive way, then you get into more complicated motion planning problems than we've given you the tools to address. You would expect trajectory optimization, for instance, might get stuck in local minima for that kind of a problem. Okay. It was actually pretty funny because we had to do this test a lot of times, and we threw a lot of 2x4s around, which is sort of terrifying. They were all balsa 2x4s because we didn't want to hurt things. But one time, the cables in our hand broke, and so we had to run through the rest of the competition with a 2x4 in our hand. Just sort of embarrassing. You like this walk of shame as you go and do the next task, and you're still holding the 2x4 from the previous task because your hand's stuck closed and you'll never open again. That was good times with the robot. Okay, so this is a kind of a more complicated motion planning problem than we've solved so far. And in general, some of the work that has happened in humanoid robotics has encouraged more and more of this sort of trying to solve relatively complicated planning problems where you're reasoning about lots of the degrees of freedom of the robot, potentially navigating in complicated dynamics and around complicated geometry. So reaching a flashlight under the chair was one of James Kuffner's early examples, and James would make the point when he would talk about this that this problem is maybe not so different than trying to solve this pretty complicated kinematic puzzle, where you're trying to, you guys have played these games, right? And where you have to really sort of figure out the magic sequence of positions in order to solve the puzzle. This, of course, at the same time as solving the kinematic puzzle, the robot also, you want it to not fall down. Okay, so we want to think about the blend of these two things. And then there are problems that are sort of in between. I would say this example is in between, where we wanted to do a UAV that's sort of flying at high speeds but through a dense forest. So this is, you could imagine, having interesting dynamics, where the dynamics really do dominate parts of the trajectory, but also interesting kinematic constraints. So when we talk about, this idea of search, what we're going to get to is planning algorithms that can address more kinematic complexity, more local minima in our basic sort of motion planning formulations. Okay, so. want to get to dynamics plus potentially complex kinematics. For instance, many links, obstacles. And I think UAV planning at high speeds has to capture the dynamics in dense obstacles has a bit of both of those. And although trajectory optimization can potentially find a trajectory for you, it can also very likely get stuck in a local minima. It decided to go left or right around the tree, and in fact, there was no solution if you went left around the first tree and right around the second tree. There was just no path that way. There was a perfectly good path if you had taken a different turn around the first tree, but because you're a local trajectory optimization method, you're just stuck in this corridor, and you're only thinking about this one corridor, right? You can imagine getting stuck with no solution. So these are nice problems that combine both aspects of this, and I haven't really given you good solutions to that problem yet, and that's the goal for this week. Okay, so let me start by introducing some of the basics of the kinematic side, which we haven't talked about yet, and we'll work back up. Okay, there's a great book on motion planning. It starts with kinematic and gets into some of the stuff we'll talk about too. If you haven't seen it, there's a book called Planning Algorithms by Steve Lavelle. It's free online. Highly recommend it. Okay, so the canonical picture in kinematic motion planning would be, imagine you have a simple robot, let's say a wheeled holonomic robot, so it's allowed to travel in all directions. You don't have to worry about having momentum or anything like this, okay? I have to drive through a little maze, let's say a little obstacle course with a few obstacles. They could be interesting geometry. Okay, let's say this is my start, and I want to get to a goal, and I just want to move a simple, let's say, a point robot through an obstacle course to get to the goal. Okay, this is the picture you'll see over and over again in the kinematic motion planning world. Now, we already have solutions to that problem, and especially when it's low dimensional like this. In fact, I basically drew the same picture when we talked about the grid world, right? When we introduced dynamic programming, we've already solved that. A form of that using dynamic programming. The strategy that we gave you back then, right, was to go ahead and just discretize the space, make a small graph on top of the space, right, and then write our dynamics on the graph, and we could solve a value iteration problem. Now, we're going to choose a slightly different algorithm this time from the motion planning literature, okay? But let's just remember what we said about this algorithm and then connect the dots, okay? So these algorithms, we could solve to optimality with value iteration. They topped out at, at 5 or 6 dimensions, depending on how coarsely you grid, but these things grow exponentially, right? This is the curse of dimensionality. But more subtle, and a bigger concern for today, would be that if you took this sort of finite discretization approach, it's not obvious that you have a sound algorithm, in the sense that I could imagine finding, making obstacle courses. Right, for which there is a path from the start to the goal, but if I just make a finite discretization, a sort of mesh-based discretization, I might label all of these cells as being in collision and therefore maybe not passable, even though there is actually a path that goes through that corridor. It's possible that my coarse discretization of the space would not find it. Okay, so for a few reasons, we haven't given you a great solution, even for this very simple problem. Here's a very simple alternative that's going to start us down the search-based philosophy path and make some connections here, okay? Okay. Instead of having a fixed coarse discretization or boxy sort of grid-based discretization, we can do a sampling-based discretization of the space. Okay. So in particular, there's an algorithm called the probabilistic roadmap. Many of you will have heard of this. Probabilistic roadmap. PRM, okay, which proceeds as follows. So you've got your complicated obstacle-ridden space. It's just going to start sampling in the space. Okay, typically just uniformly over the entire space. Just pick a point anywhere from the uniform distribution across, let's say, a rectangular box. Okay. We'll reject the sample immediately if it's in collision. Okay, so if I happen to pick a sample and I'm inside my obstacle, just throw that one away and continue. Okay. And then find your nearest neighbors. There's different ways to do this, but typically you'd say something like find all of the other neighbors, all the previous samples that you've drawn that are within some radius, and draw an edge between them. So as I start adding nodes, I'll just start connecting to the existing edges in my diagram. If my connection would go through an obstacle, then I don't make that connection. Okay, but otherwise I'm going to start trying to wire myself up to all of my neighbors. And I get these relatively dense connectivities depending on how the obstacles are arranged. oftentimes checking for these collisions across an edge is done only approximately. People will draw the straight line and then sample a bunch of times and accept the edge if all of those samples are collision-free. Oftentimes, these algorithms just assume you have a collision detection oracle. So you can ask any one point, and it'll say true or false, you're in collision, but the best you can do sort of is to sample finely in order to try to avoid collisions. There are more sophisticated versions of that, but that's the basic idea. Okay, so what you end up with if you pursue this sort of approach is that you can start building random graphs. They tend to look like this. Okay, this is the classic picture of a probabilistic roadmap, okay, which give you a sort of impromptu discretization of the space. Very different than the sort of rectangular grids that we started with, or we came up with from DP, okay? And this has a couple important virtues. First of all, once you have this graph, you can solve potentially many motion planning problems with it. People consider it a multi-query algorithm. In the sense that if I were to have made a big graph, like the one you see there, I won't continue to draw. If I now want to solve a planning problem, and I take my new starting point, and I have some graph of points here that's connected up, for instance, all I have to do is just add an edge from this to the local neighbors from my new start point and my new goal point. I can connect to whatever discretization I already have. And then I can just do graph search on this graph in order to find a path from the start to the goal. Okay? And if I have I can reuse this same discretization, this same roadmap for many queries. All I have to do is sort of connect it up, connect the dots, and I can get to new goals. You could do that with the dynamic programming too. That's not a difference, that's just an observation. Okay. This algorithm, unlike the grid world, has some notion of correctness or completeness. Okay. In the sampling-based world, we talk about probabilistic completeness. So it's probabilistically complete. Okay, so let me break that down. So what does it mean to be complete? Planner is complete if, when a path exists, the planner finds it. Conversely, if no plan exists, the planner can actually return saying there is no solution. Given a start and a goal and some configuration space obstacles, then it will say, yes, here's a path. No, there is no path. Okay. A PRM is not complete in this strong sense. A PRM is probabilistically complete. So the probabilistically complete means that as the number of samples that I draw using my discretization goes to infinity, the probability of being correct of finding a path when asked for one, and it exists, approaches 1, right? Or the probability of it failing to find a path approaches 0. People say. think, is the class that normally before this, is it randomized algorithms? I forget what, distributed, okay, distributed, okay. Wow. There's a lot of good, this is one of the good examples in robotics of, a randomized algorithm that has some properties that it's hard to obtain from a deterministic algorithm. It's kind of weird in some sense that you would do better with randomness, right? That's sort of the theme of that class, which is not the class before, so unfortunately. But this is an example of where randomization at least allows us to say something. You could say this is a pretty weak weak statement, right? It's actually fairly easy to get a probabilistically complete algorithm. The real question is how efficient it is, right? Like for many samples, how likely are you going to do it? And that's a more sophisticated argument. Okay, but this is sort of a nice example where at least trying to find a deterministic, discretization is actually potentially very hard, but taking points at random, wiring them up can give you this property fairly easily. Now, what's surprising to me is that the scaling of these methods often exceeds what people do with dynamic programming, right? So, it of course depends on the complexity of your space and how many obstacles and how, densely you end up having to pack your samples, and all these things matter. But in practice, I guess probably most problems are relatively easy, but you see people applying this, you may have applied this, in systems that are more than 5 or 6 dimensions. Maybe 10 dimensions is about as much as I've seen. David will tell you 14 is not so much a go, right? I'd say scaling, let's say, ten dimensions is sort of a common one because if you have a robot arm, that tends to be 6 or 7 degrees of freedom, and then if you maybe put it on a torso, that tends to add about 3 more. If you have 2 arms and you want to work together, probably not going to be happy. So you probably plan one at a time, and then make sure that just hope that they don't collide with each other. Okay, but that's somewhat surprising. Okay, and some of that can be achieved with stronger heuristics than that we'll talk about today. There's one other virtue I guess I'd like to point out, which probably most people wouldn't bother with, but for me it's a big deal, okay? Especially since we've talked about trajectory optimization a bunch. One of the things I really like about these algorithms is that if you think about, I've made a graph, and then I have a new start and a goal, and I just do any of my favorite graph search algorithms sort of to find that path. The length of the path in terms of the number of segments in my discretization is whatever it needs to be to find its way from the start to the goal. Okay, that sounds like such a silly thing to point out as a virtue, but it bugs me deeply that our trajectory optimization algorithms typically don't have that property, right? Our trajectory optimization, you say, I've got n equals 41 samples. I'm going to move them around and try to satisfy my constraints. And maybe I'll stretch and shrink the path between them. But there's something sort of, I think, fundamentally missing from our trajectory optimization algorithms that we have to encode ahead of time exactly the number of steps it's going to take to get to the goal, even though the goal may be in very different locations, and we might have to figure it out. So, the number of samples in the solution path, let's say, is unknown, is unspecified. I like this very much. I think that should be a goal. If you think about these problems like through the lens of optimization, I think the fact that we require a certain number of samples in our trajectory optimization probably adds some artificial badness or hardness into the problem. It's like a weird constraint that we're stuck with just because of the contract we have with our solvers. And this is in some ways a much simpler algorithm, but it's a more flexible notion of what a path should be. Now, this notion of completeness it's almost a cultural thing. So like I said, these things came down from a branch of planning and AI that was more worried about properties like completeness than, for instance, optimality, right? So there are versions of this now that talk about finding the shortest path, and they talk about asymptotic optimality and the like. There are versions that can sort of bring cost functions back in, but the focus in the community has been more about completeness and about fast incremental sort of algorithms, and less about optimization and optimality the way we've talked about. Okay, so that's just a very basic kinematic motion planning. What about if we have dynamics? What if we're, will this solve like the pendulum, or this is my litmus test, right? Every time we've got a new algorithm, like, okay, make sure it solves the pendulum. Okay, good. Now the acrobat, right? Now, and you sort of go through the recipes, right? How does this algorithm apply to, let's say, the pendulum? And you'll see, actually, it gets pretty funny pretty fast, right? So let's say I'm in the phase portrait of the pendulum. If I have to, now I have to discretize state space, not just configuration space. Then how does it work, right? So let's say I draw some random sample, okay? First sample is there. I've got a graph of size 1. Now I grab another sample here, okay. Well, already you can sort of think, okay, I can imagine connecting those two up, that's okay. But the notion of it being an undirected graph seems already broken, right? I can imagine going from here to here, but going from there to there just doesn't work in state space, okay? So we have to go from a directed graph, an undirected graph is now a directed graph. But it gets even more funny, if you will. So let's say I pick now this point here, okay? By any simple distance metric, this point here is probably closer to this point than this point. So if I were to try to just connect up my neighbors, I would try to connect from here to here, but you can't get there from here. Not straight, not right away, right? The only way to get from there to here might be to go all the way around and go to here, right? Even though they're very close in terms of state space, the distance could be very far apart. So our very simple recipe of just finding your nearest neighbors suddenly feels like a much harder problem. And in fact, it's a major reason why these algorithms struggle out of the box to do this, okay? So, this distance metric, if I have x1 minus x2 in state space, small does not mean that it's reachable. Okay. So these problems just sort of motivated another version of this algorithm that handles directed graphs and reachability and some of the dynamic constraints a little bit better. And that algorithm is called the rapidly exploring random trees algorithm, RRT. Okay, so once dynamics and sort of reachability and you know, having constraints starts to dominate. I mean, RRTs are useful even for kinematic motion planning, but they were originally motivated. If you talk to James and Steve Lavelle, who introduced them, they were originally motivated by these problems of from now it's on.
Yeah, I can,
Yeah? Okay.
I can hear you.
I'll stay close to this board and not tether myself to the table. Okay. There's a couple super interesting things to understand about the RRT. Even in the space of, stop that from animating, okay? Let's think about some of the nice virtues of the RRT, okay? Or even analysis. It's also probabilistically complete. But what's impressive about it actually is a very important property, which is called the Voronoi bias. Okay? So who knows what a Voronoi region is in a, let's say, a Euclidean space? You know, if I have a graph in a Euclidean space, what's a Voronoi? Yeah.
For a bunch of points, the Voronoi region for a point is like everything where the closest point is that point.
Exactly right. So if I have a 2D space and a bunch of points, which would just be my nodes in my tree, for instance. Okay, then if I want to ask what's the Voronoi region for this point, it's all of the parts of space for which this point is the closest. So it requires some notion of a distance metric. If I just take the Euclidean metric, then I would expect, for instance, anything, the line exactly between those 2 points would be a defining part of my Voronoi region. Similarly, here, here, you get these partitions that look like this, where this whole region here has points for which everything in this region is the Voronoi region associated with this point. So for every point in that region, this is the closest point. Okay? And I could have another one, for instance, here, the Voronoi region for this point. So the RRT has this amazing property, if you will. It's a very simple algorithm, but it has an important step. That pick a random point and grow towards it is an important step, which gives it this property of sort of the Voronoi bias. The Voronoi bias says, first of all, that the probability of expanding some node is proportional to the volume of the Voronoi region. Okay? Why is that so magical? Okay. What it means is that if you run the basic version of these algorithms, which I can do here, if I run just the simplest version of this algorithm, just an open space with a bunch of, I put sleep in my code everywhere so that it runs slowly enough that we can watch it happen. Okay, then what you get is a graph that starts growing out. Okay, it was even too fast for me here. If you start growing this from an initial point, okay, then very quickly this thing expands out to try to cover space. And then very slowly it sort of comes in and fills in the details and gets a more and more intricate network of possible edges into the smallest possible spaces. Okay. That's what gives this very nice property of rapidly expanding to fill the space, and then filling in the details after the initial expansion has sort of covered the space. And it's not something that you get for free, okay? So here's the Voronoi regions being drawn as it expands. Okay, so you can imagine that as it grows at the fringe, these places have large volumes. If I just sample uniformly over the grid, then the probability of sampling, of course, is proportional to the volume of the associated Voronoi region. And since I'm going to expand from the closest node, that means the probability of extending that edge is proportional to the volume of the Voronoi region. And it has this magical property that it will grow out, quickly making the big Voronoi regions smaller. And then at some point, when the sort of innermost regions are large relative to receive a relatively larger sampling probability, they will eventually grow in and we'll get this vine-like structure. And this doesn't come completely for free, right? So if you would think a very similar algorithm would be start with a tree, pick a random node on this tree, and then grow it in a random direction. That sounds like almost the same algorithm, okay? But it ends up with this naive sampling. You get these hairballs of trees that are right on top of each other, and they don't have this beautiful property. Okay, so this idea of picking a goal at random and shooting towards it gives us this beautiful Voronoi bias property. This fast coverage. And the algorithms are like surprisingly effective in high dimensions. So, this was back in like around 2000. James Kuffner made this video of a humanoid. Computers were slow back then, right? And he's already solving these like very high dimensional kinematic planning problems. Now this one has dynamic constraints. It's actually, now enough to understand this completely. So he actually just plans the trajectory subject to a constraint that the center of mass always stays over the center, over the support polygon. Okay, and he only plans in the positions of the robot in order to reach down. And then in order to execute the plan, he will speed up the trajectory. He'll execute that at whatever the largest velocity he can manage that keeps the zero moment point inside the support polygon. Okay, so he uses ZNP as a constraint, a rate limiter, roughly to execute a dynamic plan as he's moving his body around. Okay, so does this work for the pendulum? I still didn't answer the basic question. Does this work for the pendulum? The answer is yes, this works for the pendulum. So if you start growing sort of an RRT using pick the closest point, expand towards it, that even though the distance metric is bad in the way that I drew, it will eventually grow from enough different places and try to extend out in enough different ways that will eventually sort of grow up and fill the space in a way that once again finds, I think another litmus test for me is, does it find the eyeball, right? Like if your algorithm doesn't somehow capture the dynamics of the pendulum, then we've failed. This very simple algorithm, just by extending through the dynamics of the system, will carve out only feasible trajectories of the system and eventually find the eyeball. This is a small variant of the algorithm where you actually grow backwards in time from the goal and forwards in time. It's a bidirectional RRT. That's why there's two different colors here. One's growing backwards, one's going forward, and that just, instead of finding a needle in the haystack of finding the goal, you just have these two trees have to collide. That's a much faster way to find some path from the start to the goal. Okay, so that's satisfying. It works for the pendulum. Does it work for the carpool? Yes, but the more you try to apply these to dynamical systems and with interesting dynamics, the more painful you will, it is to sort of watch it continuously. The pain point of this distance metric and this inefficient expansion, and it'll constantly try to like sample here, expand from this node, even though it's expanded that node a bunch of times, get these like really dense, inefficient growth compared to the beautiful growth you get in the open kinematic plans, okay? So in order to make these things work for dynamical systems, we have to bring in some more thoughts about dynamics, okay? You would not be able to solve in any reasonable time, a 12 or a 10 degree of freedom sort of planning problem with hard dynamics with these methods. Okay. Now I write heuristics here. I actually think the last 20 years of sort of sample-based motion planning has been a lot of heuristics. We have the couple basic algorithms, the PRM, the RRT. There's a few fundamental improvements on there, but there's just a grab bag of heuristics where people have found different ways to sort of potentially put things together. And I think I'm optimistic that we're gonna continue to understand sort of the right way to do these things. But let me tell you today about a few of the best heuristics. Okay, so there's 3 big steps of the algorithm. Each of them can be better, I think. The first, when we choose a random x, right, then we can improve this by saying, find maybe if we can have a better sampling distribution. Then we can potentially, do better for a dynamical system. So one of the things that feels obviously bad is that if I start sampling uniformly in the state space and my tree is only sort of near the bottom of the pendulum, then those samples are just kind of wasted samples. We're asking it to grow somewhere it has no chance of growing, so its best attempt is just going to be sort of not achieving the exploration that we hope for. If we could bring our sampling in to be more targeted sampling, on the path to the goal and maybe where it's capable of expanding, then we potentially stand to benefit quite a bit. Okay. We have this sort of find the closest point step. And here, having better distance metrics can really help. And then, choose a U to expand or extend. This is a control problem, as you correctly pointed out. This is, So the way we win is take these simple, beautiful algorithms and apply more about what we know about dynamics and control, I think, to make these steps better. Now this is my bias for this class, is to use our dynamics and control hats to make these better. I should, you won't be surprised that I think the last few years I've seen quite a few people using learning for each of these steps too, right? To try to learn a better sampling distribution from repeated planning experience, learn better distance metrics, learn better controllers, use RL, for instance, to have your expansion. You'll find all of these in the literature over the last few years, okay? But I think we can do pretty well with the tools from this class here. All right, so let's think a little bit about what makes sense I'm gonna do the distance metric first, okay? What makes sense as a distance metric for an underactuated system? Is the basic setup clear? Yeah. I mean, if you say what is a distance metric, what is the proper definition of a distance metric? A distance metric has to have, a few properties. A distance metric D, that's taking the distance between x and y should be always positive. Positivity is one of the big requirements for a distance metric. Ideally, you'd like it to be symmetric. I think we know already that we have no chance of this. I tried to illustrate that a point, if I'm an airplane flying this way and I'm currently here with large velocity, then the points over there are just not. I'm not going to be the same distance to this point as this point is to me backwards, right? Momentum means that the distance metric is not symmetric. So here we have sort of no hope, I think. So we do, at best we can do an approximate distance metric. Triangle inequalities. Are the last, desirable thing. So, there's a lot to be potentially asked for in a distance metric. What can we reasonably expect? How should I define in my pendulum example here, theta versus theta dot? What's a reasonable way to define the distance between x and y? Right, knowing fully that there's going to be multiple y's in some tricky cases. Yes?
You take the minimum time possible subject to constraints.
Awesome. Okay, so one proposal would be, let's say, the minimum time path from y to x. I actually love that suggestion, right? Yeah, the time is a perfect. You could choose any cost function, but I think time is probably the most natural one. But in general, I think the solving for even the distance between 2 points is solving an optimization problem, an optimal control problem, right? Find me a u that is feasible, subject to the dynamics that will get me from here to here in, for instance, minimum time. Okay, so the distance is a solution. An optimal control problem. So the trick is, if we have to solve the entire optimal control problem in order to get a good distance metric, is there some sense in which approximate distance metrics or approximate solutions to the optimal control problem are more obtainable than solving like the big hard optimization? Because otherwise, if we could just solve the optimal control problem, we would have been done, right? Okay, so here's the favorite example. I think that is a very satisfying solution to this for instance, UAVs flying around obstacles. Is from Emilio Frizzoli's thesis, actually. He had a thesis in a paper in 2002, for instance, okay, where he did obstacle avoidance for dynamic helicopters and ground vehicles too, okay? And he made a very simple observation and a very simple proposal. He said, we're going to pick a configuration X, try to expand all the nodes in the tree, okay? In terms of increasing cost J, and apply the optimal control policy J, okay? So optimal control policy pi. So this was his basic observation, is the cost to go function for the helicopter flying with no obstacles, which you can solve exhaustively once, can be a very good distance metric, can provide a very good distance metric for a helicopter flying around when there's trees and buildings to avoid and stuff like this, okay? So if you spend, one time solve the unconstrained problem, he solved it with value iteration on a big mesh, right? So how can you solve value iteration for a helicopter on a big mesh? Well, okay, you have to exploit the fact that there are symmetries in the problem to reduce the dimensionality, like we've often done. So if my helicopter is at position, X, and I translate the position X, the dynamics are the same, so I can just solve that optimal control problem independent of X, and then translate the solution, drop a dimension, okay? And he did all these tricks. Same with yaw. Yaw angle should drop away. Only a handful of the variables actually matter in the total value iteration solution for the unconstrained problem. They all matter in the constrained problem, okay? But he was able to, even in 2002, computers were slow, solve a one-time expensive dynamic programming approximation of his value function. Okay, and then now he wants to fly quickly through obstacles and everything. Now he draws a sample. He asks the cost to go of the unconstrained problem, which are the closest points, and then he grows from there. And how does he grow from there? Exactly like you said, he uses the policy that came from the optimal controller in order to do the extend operation. Okay, this is, I think, still a very satisfying way to do that expansion. Okay. So. Let me see, obstacle 3. Instead of unconstrained. And he was able to do real-time planning with that setup. So growing the tree with these you notice also that the tree he illustrates here and the trees that he got out of his algorithm were characteristically very different than the trees I just drew that were super dense, right? These are relatively sparse trees that take long winding trajectories because you can trust your dynamics, your distance metric and your controller to take relatively longer extends operations, okay? So you can have relatively much fewer samples in order to get around this and do everything on the fly, on board these days. There's a bunch of variants of this, so that seemed a little bit helicopter or ground vehicle specific, and you had to find a way, you had to exploit the symmetries, solve a value iteration problem, okay? There are more generic versions of this. We had a version back in the day that would solve an LQR problem, for instance. You take the cost to go for the linearized system in order to come up with a distance metric for the nonlinear system, okay? There's a few variants on that could work. Now, the minimum time problem and the cost and the LQR problem are not the same. So if you want to do a minimum time LQR, then you have to do a little. It's not just solving a Riccati equation. It's solving a small time varying Riccati equation. It's a little bit more effort, but you can make that work, and that gives fairly strong. So at least the notions of face portraits and your velocities. The fact that things move around this, in a circle in phase space, LQR linearizations can capture that, right? Even if they don't capture the full nonlinear dynamics. Again, since you're linearizing not only about fixed points, you end up doing the time varying linearization in order to do that, but you can solve that kind of problem without too hard. And there's a lot of good examples of different heuristics that, like I said, of using simple to solve cost to go functions that are surrogates for the online cost to go of the actual system flying around obstacles. Okay. So that's a quick notion of how you can do better with better distance metrics. Yes?
Are there known conditions for how good the approximation needs to be for the cost to go for the algorithm to work? Or
So the question was, are there known conditions on how tight the approximate optimal control, or approximate distance metrics has to be for the system to work? I think not. I think there's a gap in our theory here. The types of series that has gone behind this are, for instance, asymptotics analysis, saying that it will eventually, with probability 1, find a solution. That was in the original papers. People have talked about asymptotic optimality more regularly. But I think we really, and the case is almost always trivial there, where any distance metric that doesn't go degenerate will give you asymptotic optimality or convergence. So the real question is rates. Right, and the world is ready to do that now. I think we have so much more understanding about how to do finite time bounds on these things. Machine learning has given us great new tools for that. I have not yet seen people apply those tools nicely to this setting. Has anybody seen that? I haven't seen it. If anybody's out there sees it, tell me. Yeah. I think that's a great problem, waiting for better answers. Right. I mean, the full glory of it is going to be hard, but I could imagine in simple settings, starting to apply some analysis to try to get a sense for that. Okay, let's think a little bit about sampling distributions. All right, so what could you potentially do to do, what's a natural sampling distribution for a dynamical system, right? So again, this is now, it's a heuristic, but the thing I think that the RRT wants is for someone to draw samples just beyond what it's currently doing, right? So I'd like, if I have a start and a goal here, I would like somebody to tell me to sample for places that are just beyond my current horizon. I've got branches of my tree ready to go, and certainly in the direction of the goal, but eventually everywhere, because I might take a circuitous route to the goal. Okay, but there's some notion of samples that I just can't get to right now are useless samples, and I'd like to sample from the places where I can get to in a single step. Those are going to be the effective samples. All right. So that brings in this better sampling question naturally connects, I think, to the notion of reachability in dynamical systems. Sampling should try to, 1, explore the space, 2, direct me towards the goal. But most importantly, I think, and most missing, is somehow be reachable from my current tree. We have seen empirically, I think it makes sense intuitively, and we've seen empirically that drawing samples sort of from the local reachable set of the existing tree can be a much stronger way to grow these trees effectively. With many fewer samples, you can get much better coverage. Okay, so if I'm in phase space and I'm here, there's a notion we've brushed up against but never really focused on about reachability analysis, okay? That for a pendulum, let's say, it might be that there's some set of states here that I can visit in a short amount of time, okay? And reachability analysis is closely related to Lyapunov analysis, okay? Lyapunov analysis looks backwards from the goal. It tries to find, the Lyapunov function tells me all the states that can potentially converge to a goal, for instance. Reachability analysis is, you can use the same Lyapunov-like functions to talk about from a point, where am I going to be able to get to in some finite amount of time. That would be they're very closely connected to Lyapunov functions. The one time we talked about it a bit was when we talked about the funnels, remember? When we talked about the time-varying Lyapunov functions, and we had time-varying Lyapunov functions that were going backwards in time, but we also had the exact same definition of funnels could give me a forward reachable set from some small set of initial conditions. I can talk about growing myself to the biggest possible region. All that changes in this computation is changing the constraint to be I'm going to start from an initial point and I'm going to maximize the set of possible states, but I can still search for a Lyapunov function such that I'm going, I can always go downhill. All the same math works to talk about reachability analysis. And there are a lot of special cases where people have closed form solutions for reachability analysis. Okay, so for instance, in linear systems in your discrete systems, it's relatively easy. Typically, in particular, if you talk about with ellipses or polytopes. If you tell me I've got a set of states defined by the interior of some ellipse, and I push it through a linear system, and I have ellipsoidal constraints on my control inputs, then the set of possible states is also an ellipse. It's just like a Gaussian propagates through a linear system. The sublevel set of a Gaussian pushes through, an ellipse does. Similarly, if you have a polytopic region and polytopic constraints, you can shove that through a linear system and you get polytopes around. So you'll see lots of people drawing pictures with either reachability sort of either funnels that look like ellipses or they're polytopes that are pushed through a linear system to give you another polytope of the same cardinality, the same number of faces. It'll push through a linear system. Okay? So there's lots of tools that we've brushed up against but haven't fully explored about reachability analysis. And my claim is that that's the stuff you need to find a good sampling heuristic for these algorithms. And to convince you, I'll show you some simple examples of that where we just really coarsely approximated the reachability analysis just by throwing a few points out, okay, and then just making, let's say, a polytope around that. Very approximate. We've done more exact things since then, but I'll tell you exactly how it works in a second here. But this is a basic RRT using a standard metric and a standard sampling distribution. This is now a reachability guided RRT. You'll see lots of papers that have that, something about reachability associated with our RRT. And the expansion, this was given many, many more samples to eventually find its path to the goal. This one finds its path to the goal with many, many fewer samples. So it has a much sparser tree that expands only on the fringes of the frontiers of the reachable set here, and it finds the goals, in bigger problems or with fewer samples in the simple problems. Okay, so this is a nice way to see sort of that work, how that works. Okay. So in this particular version of the algorithm, a reachable set was approximated just by a handful of points. And the algorithm goes like this. It says, pick a point at random. If the closest point is a reachable point, okay, which is one of these pink regions, the green boxes here are the Voronoi regions associated with the reachable points, the pink points, okay? Then I'm going to go back to the point that it was obtained from, okay? And I'll expand that node. Every time I expand a node, I'll fire out a few more pink points, okay? So I have a pink tree that's always growing on the frontiers of my blue tree, which is the actual RRT tree, okay? But only when the pink points are closer, the frontiers, which I have not yet explored officially, are closer to my sample, will I actually expand from that sample. This is like a very RRT way to approximate a reachable set. Okay. Just use nearest neighbor to a point calculations to try to understand the reachable set, to say that this is the frontier that I should expand, and you expand from that node. Did I say that well enough? Maybe no. Okay. Every time I add a node to the tree, I'll cast out a few samples as if I were to hypothetically simulate this forward a few more times, I get these pink nodes. I'm not going to add all those pink nodes immediately to the tree, because then I'd have this super dense, fallen on itself tree. Instead, I'll keep those marked as separate. These are my reachable frontiers. And then when I do my random sample in the entire state space, if my frontiers, my reachability frontiers, are closer than any point that's actually been added to the tree, then I'll accept that candidate. I'll try to grow in that frontier. Okay. And this has the property now of really only growing on the frontiers, the places where the unexplored regions that the reachable sets cover that the original sets didn't cover. And that type of thinking, there's been many papers in the line of sort of using these types of heuristics or exact reachability computations or anything in between to try to more effectively grow these trees in state space. Back in the day, that was enough to plan dynamic trajectories of little dog bounding over rough terrain, which we just couldn't write a controller for ourselves. Okay, we used only an approximate model of the robot. Okay, that was definitely an approximation, an approximate notion of the terrain, but for a particular terrain, we could plan a specific set of bounding gates in order to bound over that terrain. Too slowly to run online, right? So all the NPC stuff that's been happening more recently in quadrupeds is much faster than this. This was like an offline computation. We were happy to find it ever. Okay, and then just to finish up with this part of the conversation, so there's lots of good things that you can do for better control. Okay, so if I were to say I found two samples that are somehow far away in my state space, then it may or may not be worth the effort to run a full trajectory optimization to try to connect the two. Okay, so you can use, again, it's a common thing to see, is to use trajectory optimization as an inner loop for RRT to extend. And in that case, as long as your trajectory optimization, will eventually succeed even when the trajectories are short, if your trajectory optimization isn't super reliable but has some basic properties like when the problem is simple enough it will eventually succeed, then this can be a very fruitful combination as long as you can make your trajectory optimization fast enough. So a lot of the early work on trying to do dynamic RRTs would use trajectory optimization and realize that that's a pretty slow inner loop, okay? But as you speed up your repeated solves of trajectory optimization, you do some clever warm starting and things like this, then using a trajectory optimization can certainly be a nice way to warm start. There's a lot that you can do to make this better, so a lot of clever tricks here. So let's say I'm growing from here. Let's say I decided to try to expand from here to here, but my system is potentially, or my trajectory optimization is too weak to get all the way there. I found that it's very useful to write a final tree constraint, if you will. So if you pick, you say this is my, I've got a random sample. Do I grow all the way from here to the random sample? Or from, this is my closest point on my tree. Do I grow all the way from here to that random sample? I find it much more effective in trajectory optimization to, instead of constraining to go, say I'm going to go exactly from this point to exactly this point, that's a hard 2-point boundary value problem. We have the flexibility in trajectory optimization to say, my initial condition, for instance, could be anywhere along the existing tree. So if I have a whole dense network of possible solutions in an existing tree, rather than say, okay, this was the closest point, only grow from here, allow my trajectory to connect up anywhere along the continuous existing paths in the tree. Okay? So you can write a more advanced constraint in your trajectory optimization that allows the solution to not only connect at the joints, but to connect anywhere along the continuous paths of the tree. And that can make trajectory optimization much more effective. Okay, so that's a few of the types of ways that I think the dynamics and control stuff we've already talked about connects into these random sampling-based algorithms. And it opens the door, I think, so on Thursday we'll give, I think, maybe more complete connections between these things. But I really think there's a few really good things that happen when applying these sort of search-based algorithms and combining them with the dynamics, right? So effectively, if I wanted to have a complicated dynamical system, fly around obstacles, we just couldn't do it before, and we can do it in reasonably high dimensions, even with real-time obstacles with these kind of tools. There's extensions for hybrid systems, all these things. Yes?
I was going to ask about the hybrid system.
Yeah. So for instance, so because of the connections to reachability analysis, connections to trajectory optimization, like one of the hard things about hybrid systems, in my canonical picture of hybrid systems here, it's very hard to know what's the distance metric from here to here. The hybrid systems language roughly says there's a black hole, somehow between here. You have to teleport through this wormhole, not black hole, wormhole. Right, so how can you possibly write a distance metric across that? If you can do reachability analysis through there, for instance, the very simple version I just showed, right? If I had a point here that, blue on my original tree, right, and I cast some red points across, and knowing that I'm close to this red point would actually tell me to project a blue point through the wormhole and can solve some of these challenges in hybrid systems. That's why it worked. The little dog robot hopping was a hybrid system, and that reachability based algorithm did work through hybrid systems in that way. Trajectory optimization can go through the hybrid systems in the way we like. And also, there are ways to write contact-based hybrid systems where the distance metric is more clear than in the full. There are, like the floating base coordinates is actually a better notion of distance, I think, than the minimal coordinates version, right? If you have my compass gate walker, for instance, if it's just changing coordinate systems on impact, then it's very hard to write a metric across that. But if you use the formulation where you're in a floating base coordinates, you're using all the same joints and all the same in all the different modes, you're just turning on and off constraints. Then the notion of distance is more, at least it's in the same state space, for instance. It's a great question. Cool. I put up some office hours tonight, and I will put more up if people ask for them, and I'm enjoying answering your questions on projects. See you soon.